Well, usually when we think about the future of cities, the images that come to mind are highly physical.
Right. Yeah. Tangible things.
Exactly.
Right.
We picture the concrete, the glass, maybe those vertical forests scaling the sides of massive skyscrapers, or, I don't know, reimagined transit systems physically moving millions of people around.
Yeah, it's a very structural vision.
Right.
We are naturally drawn to what we can touch.
Which makes perfect sense because historically, urban planning has always been an exercise in manipulating physical space, right? Moving resources from point A to point B.
Building roads, managing density through zoning, that is the traditional domain, yeah.
But, and this is where today's deep dive comes in, you step into the actual architectural research regarding the urban ecosystems of tomorrow, and suddenly that physical infrastructure takes a massive backseat.
It really does. It's almost entirely invisible.
Right. We're looking at an invisible landscape. I mean, project yourself just a few decades forward to the year 2050, where over two-thirds of the global population lives in urban areas.
Now we're talking about megacities here.
Yeah, a megacity being defined as having over 10 million inhabitants.
Yeah.
Managing that scale is no longer a physical challenge, it's a software challenge.
Absolutely. The sheer density forces a complete reimagining of how a city functions. 10 million people means tens of millions of daily transactions, movements, resource allocations.
It's just a mind-bogglingly complex digital nervous system.
Yeah, you cannot manage a grid of that magnitude with localized, siloed systems anymore. A few times traffic lights and a, municipal scheduling book won't keep the city running.
No, not at all.
So the concept of the smart city, as defined in our source material today, completely departs from the idea of just installing cool gadgets on street lamps.
Right, it's not just smart bulbs.
No, it is defined as the seamless integration of physical infrastructure with social, environmental, and economic factors all glued together by ICT.
Information and communication technology.
Exactly. ICT is the absolute bedrock.
It provides the software systems that deliver every digital service you interact with as a citizen. But the catch, and this is where the research paper we are unpacking today really anchors its thesis. None of these digital services can exist in isolation.
They require a constant exchange of data.
Right, across a wildly fragmented software ecosystem. It's a massive web of dependencies.
Yeah, like a private retail business needs to talk to a public municipal service.
Or a health provider needs to talk to a transit authority. Let's actually ground this in a scenario for you listening. Imagine you are running errands in this future megacity.
Okay, paint the picture.
So, you go to a grocery store, you buy your week's supplies, and because your transaction crossed a certain financial threshold, the shop's proprietary checkout software fires off a signal to the city's municipal parking system.
Seamlessly.
Right. It automatically pays and validates your parking ticket. There is no secondary app you have to open. You don't, take a physical ticket to a kiosk. The action just happens in the background.
And that interaction relies on two completely disparate entities communicating perfectly.
Which is wild to think about.
It is. You have the private, profit-driven retail ecosystem interfacing directly with a public, heavily regulated municipal grid.
Right. Or let's look at a public-to-public interaction from the text. An elderly resident has a scheduled medical examination at a specialist clinic.
Okay.
The moment that appointment is confirmed in the municipal health database, a signal is routed to the public transit system, or maybe a subsidized private rideshare fleet.
And it just books it.
Yeah, a vehicle is automatically booked and timed to arrive at the resident's home.
Yeah.
And it even factors in real-time traffic density data across, like, a 5-mile radius.
Wow.
To the end user, it feels completely frictionless. It feels like magic.
But it's not magic. The research refers to the mechanisms enabling that as integration process.
Integration process.
Yeah, these are the invisible threads, the dedicated middleware connecting all these fragmented digital services.
Because they weren't designed to talk to each other originally.
Right. Exactly. They are highly specialized software tools whose sole purpose is to translate, route, and deliver data between platforms that speak completely different languages.
So the mission for our deep dive today is to really pull back the curtain on those integration processes. Because the moment you have thousands of distinct software systems talking to each other at the speed of light, you introduce rules.
You have to. You introduce restrictions, service level agreements, data limits.
Right. So we have to figure out what happens when these automated, lightning-fast interactions are bound by strict contractual obligations. How do you monitor the rules of millions of automated interactions happening every single second without a human sitting there watching a screen?
Well, the scale makes human oversight completely impossible.
Yeah, you need an army of IT people.
And they still wouldn't be fast enough.
Hmm.
So the source material proposes a highly specific, novel architecture to monitor these interactions using smart contracts.
And we need to dissect how this proposed system works.
Right.
Look at why the current monitoring technology we all rely on today falls completely short.
And examine how this new framework acts as the invisible automated referee for the smart cities of tomorrow.
Okay, so before we get to the referee, we have to understand the playing field. Let's look at the anatomy of an integration process. How do these digital services actually, pass notes in class?
Well, an integration platform provides the environment. It's the suite of tools developers use to create, test, and run the integration processes.
Okay.
And once an integration process is live, it essentially acts as a dedicated intermediary. The paper deconstructs this intermediary into two primary operational components.
The tasks and the ports.
Exactly, the tasks and the ports.
Let's start with the tasks, because they handle the actual payload, right?
Yeah. When data flows through an integration process, is packaged into messages. And tasks are the internal operators that manipulate those messages.
They're the ones actually doing the work on the data.
Right. They execute atomic operations on the data itself. The paper outlines a variety of these operations, like a task might filter incoming data, stripping out personally identifiable information before passing it to a public database.
Oh, okay. So it's protecting privacy.
Yeah. Or it might merge two separate data streams into a single profile. It might split a large, complex message into smaller, manageable parts.
Just breaking it down.
Exactly. It handles data format transformations, copying, aggregating, routing the message to its final destination.
I sort of picture this like the internal operations of a massive exclusive VIP nightclub.
Okay, I like that.
Yeah, so the tasks are the internal event staff. Once the guests who represent our data messages are inside the building, the staff completely controls the flow.
Right, they direct people around.
Exactly. They direct a certain group to the VIP lounge, which is routing. They pull individuals from different tables to form a new group on the dance floor, which is aggregating.
That's a great analogy.
Or they might tell a large group to split up to fit into smaller booths. The tasks handle all the chaotic manipulation of the environment once the data is already inside the system.
And that internal control is vital for the data to be usable by the receiving end. But to even get into the nightclub, the data has to pass through the port.
Ah, the port.
Yes. The paper defines ports as the implementations of communication protocols. They abstract the interaction with the external digital services.
It mentions specific protocols, right?
It signs protocols like HTTP for standard web traffic, FTP for file transfers, SSH for secure remote operations, or JDBC for database connectivity.
So continuing the nightclub analogy, the port is the bouncer at the front door.
Exactly.
It's the loading dock for the caterers. It is the definitive point of entry and exit.
Right. When an external municipal service wants to send a package of data into the integration process, it can't just throw it over the wall.
Right, can't just barge into the club.
No, it has to walk up to the bouncer, present the data using a very specific agreed-upon language, which is the protocol and request entry.
So the port is the absolute interface with the outside world. It handles the handshake.
Yes.
But here is where the architecture gets tricky and where the research paper really zeroes in. If the tasks are doing the heavy lifting, if they are the ones actually formatting the hospital records or merging the transit schedules, it seems like that should be the focus.
You would think so.
Right. So why is the entire monitoring philosophy proposed in this paper obsessed almost exclusively with the ports?
Because the tasks are purely internal. They operate in a completely controlled, isolated environment. The ports are where the integration process is exposed to the chaos of the external world.
The Wild West of the internet.
Exactly. And critically, the ports are where the restrictions of the system are applied and challenged.
Okay, right. So the bouncer isn't just checking if you have an ID. The bouncer is enforcing the fire code.
Yes, perfect. When you link a private grocery store's checkout system to a municipal parking database, you don't just open an infinite pipeline and say, hey, send me whatever you want, whenever you want.
No, that's how systems crash.
Exactly. You establish strict rules of engagement, and the paper details several types of limitations. There are rate limits, which is a maximum number of requests allowed per unit of time.
So the parking system might say to the grocery store, you can only ping my database 100 times per second.
Right. And request 101 will be rejected.
Makes sense. Or there are maximum response times. If the transit authority requests data from the hospital to book that taxi we talk about, and the hospital's server doesn't reply within, say, 50 milliseconds, the interaction time's out.
Yeah, it's deemed a failure because the transit algorithm cannot wait. It has to move on to the next routing calculation.
You also have data volume restrictions, right?
You do. A system might cap the maximum amount of data transmitted per request to prevent bandwidth hogging. These limitations are the guardrails of the megacity.
Because without them, what happens?
Well, without them, a single malfunctioning app could flood a municipal API with requests, effectively executing a distributed denial of service attack on the city's infrastructure.
Just accidentally taking down the city grid.
Exactly. So these guardrails are essentially contractual obligations. They are terms of service agreed upon by the different software developers.
But again, we run into the scale problem. You cannot have human compliance officers sitting at thousands of digital ports watching a dashboard to ensure the grocery store hasn't exceeded its request limit.
No, the human element has to be entirely removed from the enforcement mechanism. And this introduces the concept of the smart contract.
Right. So the paper defines smart contracts as self-executing software programs that enforce contractual terms without human intervention.
They utilize programmable logic to strictly define the rules, conditions, and penalties of the agreement between the communicating parties.
They represent the digital automated evolution of legal agreements. Instead of a written contract sitting in a filing cabinet somewhere, the terms are translated into executable code.
And the paper specifies that these contracts are generally written in cross-domain programming languages like Solidity or general-purpose languages like Go.
And the defining characteristic, the thing that makes a smart contract more than just a standard if-then statement in a random piece of code, is where it lives.
Exactly. It is deployed and executed on a blockchain platform. The researchers specifically evaluate contracts running on Ethereum and Hyperledger Fabric.
And why a blockchain?
Because the blockchain provides immutability. When the grocery store and the parking authority agree to their data sharing limits, that smart contract is published to the distributed ledger.
Meaning neither the grocery store nor the parking authority can secretly alter the code to give themselves more bandwidth later.
Exactly. It acts as a shared, transparent, cryptographically secure source of truth.
Okay, so we have the communication ports handling the massive influx of data, and we have immutable smart contracts sitting on a blockchain defining the exact rules of how that data can behave.
Right.
Conceptually, it seems like the problem is solved. Just connect the two.
Right, just plug them in.
But the core premise of this research is that a massive technological blind spot exists right at that intersection.
Yes. The current landscape of monitoring tools simply does not account for this specific cross-section of technologies. The paper states unequivocally that existing tools lack the dual capability to simultaneously observe the granular events happening at the communication ports and seamlessly invoke the corresponding smart contracts to evaluate those events.
They just can't do both.
Yeah.
Let's dissect why our current tech stack fails here. When we think of massive enterprise-scale monitoring, we usually think of two categories. The first is infrastructure monitoring, which is what the vast majority of current literature focuses on.
Yeah, infrastructure monitoring looks at hardware resources. It monitors memory consumption on the servers, CPU load, available disk space, raw network traffic.
It's entirely focused on the physical health of the machines running the software. It tells you if the server is literally on fire.
Or if a hard drive is about to fail.
Right. But it knows absolutely nothing about the business logic. It doesn't know what an Ethereum smart contract is, let alone whether a specific data packet violated Clause 4, subsection B of a transit agreement.
It's completely blind to that. The other category is application performance monitoring. And this looks inward at the software itself. It tracks the execution of the internal tasks we discussed earlier.
The event staff inside the club.
Right. It can tell you if a message was successfully filtered or if a database query was slow. But again, it is largely blind to the external blockchain-based contractual obligations that govern the port.
Okay, so the researchers bring up specific, incredibly popular tools to illustrate this gap. Let's look at the open source ecosystem first, because that is usually the go-to for developers who want flexibility. They mentioned the Grafana Lab Stack and Elastic.
Yeah.
Why can't a city IT department just configure a massive Grafana dashboard to monitor these smart contracts?
Well, the sheer complexity of the configuration becomes an insurmountable barrier. The paper outlines what a Grafana deployment would actually require for this use case.
And it's not simple.
No, you can't just install one piece of software. You have to build an entire bespoke pipeline. You would need to deploy Promtail agents across every single integrated application just to collect the raw logs.
Oh, wow.
Then you would need to route those logs into Loki, which is a specialized log aggregation system. Then you would have to build custom querying logic in the Grafana visualization layer to somehow parse those logs and manually trigger blockchain evaluations.
It's like the ultimate Rube Goldberg machine.
It really is. And worse, building that pipeline usually requires heavy instrumentation of the source code.
Meaning you'd have to go to the developers of the municipal parking app, the private grocery checkout app, the transit routing algorithm, and say, hey, we need you to rewrite parts of your application to format your output logs exactly the way our Promtail agent wants them.
Yeah. And in a smart city ecosystem comprising thousands of legacy systems, proprietary corporate software, and rapid deployment microservices.
Good luck with that.
Exactly. Forcing a universal rewrite of logging standards is a political and logistical impossibility.
So if the open source route is too complex and invasive, what about the commercial, polished, cloud-based solutions? You know, the big players like Datadog or Dynatrace, because they abstract all that complexity away, right? They give you a beautiful interface right out of the box.
They do solve the complexity problem, yeah, but they introduce a fatal economic flaw.
The cost.
Right. Commercial observability platforms operate on a pay-as-you-go or pay-per-event pricing model. You pay a fraction of a cent for every log, metric, and trace ingested into their cloud.
Okay, so let's extrapolate that pricing model to a megacity. You are monitoring every automated grocery checkout, every taxi dispatch, every smart meter reading, every traffic light sensor adjustment across a population of 15 million people.
You are generating billions of events a day.
Billions.
The volume is astronomical. If a city relied on a platform like Datadog to monitor the granular port interactions of every integration process against a blockchain contract, the monitoring costs would dwarf the actual operating costs of the digital services themselves.
That's crazy. A highly successful, widely adopted smart city service would essentially bankrupt the municipal IT budget through logging fees alone.
It's completely unviable.
The paper also touches on recent academic pushes to solve monitoring issues with artificial intelligence. There is a lot of literature on using machine learning algorithms to predict critical system failures before they happen, or to dynamically filter out alert noise so administrators don't suffer from alert fatigue.
Machine learning is fantastic for recognizing patterns in chaos. If an AI sees a specific spike in CPU load followed by a memory leak, it can predict a crash.
Sure.
But the researchers point out that none of these AI advancements address the specific domain context of smart contracts.
Because AI predicts probabilities based on historical trends.
Yeah, actually. But a smart contract evaluates absolute deterministic rules based on immediate data payloads. An algorithm predicting server health doesn't help an administrator determine if a specific data transmission legally breached a service-level agreement.
It's a profound realization. We have this vision of perfectly automated city, but the tools we have to ensure everyone plays by the rules are either too complex, too expensive, or fundamentally looking at the wrong metrics.
The ecosystem is incredibly fragile without a purpose-built referee.
And recognizing that fragility is what led the researchers to design a completely novel architecture. But before writing a single line of code, they had to resolve a fundamental architectural debate.
They had to choose between two competing philosophies of system design.
Enforcement versus monitoring.
Exactly.
This debate is the conceptual core of the entire paper. Let's explore the first path, the enforcement approach. If you ask a layperson how a smart contract should work, they will describe enforcement.
Right. If a rule exists and an action breaks that rule, the system should actively block the action.
In an enforcement paradigm, the smart contract acts as an active, synchronous gatekeeper. If we apply that to our integration platform, it turns the communication port into an absolute filter.
Going back to our nightclub bouncer.
Yeah. The enforcement bouncer physically stops you, checks your ID, checks the fire code, runs a background check, and refuses to let you take a single step inside until every clearance is granted.
Mechanically, when an event arrives at the port from an external service, the integration process immediately halts. It captures the event data, generates a query, and sends it out to the blockchain network to evaluate the payload against the smart contract clauses.
It pauses the business logic to ask for permission.
Yes. And if the blockchain determines that the event breached a clause, perhaps the response was too slow, or the payload lacked required authorization tokens, the operation is blocked entirely.
Just shut down.
Right. The integration process throws an error back to the sender, and the internal tasks never even touch the data.
Philosophically, this sounds correct. You prevent bad data from ever entering the system. You guarantee absolute compliance.
So why did the researchers reject this model?
Because of the realities of blockchain technology and the unforgiving speed requirements of a smart city, the researchers identified two fatal drawbacks to the enforcement model:
Which are?
processing overhead and devastating latency.
Because blockchains are not databases optimized for speed. They are distributed ledgers optimized for consensus and security.
Exactly. When you query a blockchain, especially a robust public or consortium chain like Ethereum, it is not instantaneous. The network has to validate the transaction.
So it takes time.
It might take seconds or even minutes during high congestion to receive a definitive response. Think about the implications of that lag. Imagine the transit algorithm trying to book a taxi for the hospital patient. It pings the municipal health database to confirm the appointment time.
Right.
But the integration port is running an enforcement model. So the port pauses the request, reaches out to the Ethereum network, and waits. For 12 seconds, the entire process just hangs.
And the transit algorithm times out. The taxi doesn't get booked.
If you force every single integration operation across millions of citizens to await synchronous completion from a blockchain, you create the largest digital bottleneck imaginable.
The city's digital infrastructure would completely grind to a halt. Real-time services would become impossibly slow.
So the cure is worse than the disease. Perfect compliance destroys the functionality of the system.
Exactly. So the researchers discard enforcement and pivot entirely to the second philosophy, monitoring. Or, more accurately, asynchronous monitoring.
This represents a massive shift in how we think about control.
It does. In the monitoring approach, the execution of the smart contract and the execution of the integration process are entirely decoupled. They operate independently of one another.
Let me conceptualize this. The hospital data request arrives at the port. The port simply lets it through.
Yep.
The integration process does its job. It filters the data, routes the confirmation to the transit algorithm, the taxi gets booked. The business process moves at maximum speed.
Right. No waiting.
But simultaneously, the port sends a copy of that event data to a separate asynchronous monitoring system.
That is precisely how it works. The monitor takes that event data and goes off to query the blockchain at its own pace. It evaluates the smart contract clauses in the background without ever pausing the actual flow of the city's digital services.
So this prioritizes speed and systemic flow over perfect real-time compliance.
Yeah.
But the trade-off is massive, right?
Oh, yeah. Huge.
If the asynchronous monitor checks the blockchain and discovers that the hospital's request actually breached a contract clause, maybe it included unauthorized data fields, well, the transit algorithm has already booked the taxi. The invalid action has already occurred in the real world.
The paper confronts this reality directly. It states that under a monitoring model, if clauses are breached, the integration process has already been executed, necessitating what they term a compensatory action.
A compensatory action. That is a very clean academic phrase for cleaning up a potentially massive mess.
It really is.
If the automated system allows a flawed transaction to go through just to keep traffic moving, the system accepts that it will occasionally have to reverse or compensate for real-world actions later.
It's an admission that in a sufficiently complex environment, you cannot stop every error at the perimeter. You have to let the traffic flow and, issue the speeding tickets after the fact.
Right.
The researchers argue that this asynchronous, non-blocking approach is the only paradigm that aligns with the event-driven nature of modern microservices and smart city architectures.
It is a profound architectural choice. We are building a system that watches records and reports, but rarely intervenes in the moment. So let's look at how they actually build this watcher. We are looking at the blueprints of the architecture, specifically the 5 distinct APIs that serve as the system's nervous system.
Right. An API, or application programming interface, defines the exact methods and data structures required for external entities to communicate with the software system. And the researchers designed this monitor with 5 highly specialized APIs to ensure complete modularity.
Let's group these conceptually. APIs 1 and 2 act as the foundational configuration layer, right?
Yes. API 1 is dedicated exclusively to managing the connection parameters for the blockchain platforms.
So it's the map.
Basically, a city administrator uses this interface to tell the monitor, hey, we have an Ethereum network located at this IP address and a Hyperledger Fabric network located over here. It establishes the physical pathways to the ledgers.
Okay, and then API 2.
API 2 takes those pathways and maps the business logic onto them. It is responsible for the registration of the smart contracts themselves.
So an administrator uploads the metadata of a contract, the contract's internal name, the specific executable clauses contained within it, the exact arguments or data points those clauses require to function.
Exactly. And crucially, it maps that contract to one of the target blockchains configured in API 1.
So before a single event is processed, the system knows exactly where the rules live and what language they speak.
Yes.
Then we have the ingestion layer, which is API 3. Reading the architecture, API 3 is the main artery. This is where the sheer volume of the megacity hits the monitor.
It is. When an integration port processes an external request, it fires off an asynchronous notification to API 3. This is the interface that actually records the events.
But it does not just accept raw, chaotic data.
Not at all. The paper is incredibly strict about the format. It provides a code snippet, listing 1, illustrating the exact JSON payload required.
The structure of that payload is deeply revealing about how the system operates. It requires 2 distinct sections. First, an authentication header.
Right. A city cannot allow arbitrary actors to inject false events into the municipal monitoring system. The integration process has to prove its identity cryptographically.
And the second section?
The second section is the body, which contains a highly structured dictionary payload. This payload must explicitly state the contract ID that governs the interaction, the specific clause IDs that need to be evaluated, and the precise data arguments extracted from the event that the smart contract needs to run its logic.
It is essentially the integration process handing the monitor a perfectly organized dossier.
Yeah.
I am event X, I am operating under contract Y. Please evaluate clause Z using these 3 data points.
That's a perfect way to put it. Following ingestion, we have the administrative layer, API 4.
Which operates like a traditional control panel.
Right. It manages base registration data, setting up authorized user accounts, defining user groups, establishing role-based access permissions. But it also controls a vital operating parameter, the event retry policy.
I know we will explore the mechanics of that retry policy when we look at the internal components, but it essentially dictates how stubborn the monitor should be when a blockchain network inevitably drops a connection.
Exactly. Finally, we have the output layer, API 5. If API 3 is where the city's data flows in, API 5 is where the ultimate verdicts flow out.
So this interface allows external applications, maybe a centralized municipal dashboard or an automated auditing tool, to query the monitor and retrieve the final status of any executed smart contract.
Right.
When you look at this 5-part API structure, what stands out to me is the philosophy of isolation. By strictly separating the blockchain infrastructure configuration in API 1 from the contract logic in API 2 and completely isolating the data ingestion in API 3, the researchers have created an architecture that is entirely blockchain and domain agnostic.
And that agnosticism is its greatest strength.
Because smart cities will outlive any current technology stack.
Absolutely. If a city decides 10 years from now to completely abandon Ethereum and migrate all its smart contracts to a revolutionary new ledger technology, they only have to update the connection parameters in API 1.
The integration processes feeding data into API 3 and the auditing tools pulling reports from API 5 remain completely untouched and unaware of the underlying shift.
The architecture is incredibly future-proof.
Okay, so we have defined the perimeter. We know how the configuration is set, how the data enters, and how the reports exit. It is time to look inside the black box. Let's trace the journey of a single, highly specific event as it travels through the internal components of this monitoring system.
The paper outlines 6 distinct internal components operating in a pipeline, and the defining characteristic of this pipeline is that every stage operates asynchronously, communicating via internal message queues.
Let's use our earlier scenario. The municipal health system books a taxi via the transit authority. The integration port handles the transaction and fires a perfectly formatted JSON payload to API 3. It enters the monitor. Where does it land?
It immediately drops into the first component, the inbound events queue. This acts as an initial buffer, a holding area. Because the system is event-driven, it does not force immediate blocking action. The event simply rests in this queue based on the availability of downstream computing resources.
It's a massive digital waiting room.
Yes.
And the second component, the event handler, is the worker assigned to empty that room.
Exactly. The event handler constantly asynchronously pulls the inbound events queue. When it pulls our taxi event out of the line, its primary responsibility is structural validation. It acts as the first line of defense against bad data.
It cross-references the payload's claims against the established configurations from APIs 1 and 2.
It checks the paperwork. The paper categorizes the exact ways this paperwork can fail, grouping them under structure integrity category exceptions.
Instead of just listing them, let's look at the logic behind these failures. The event handler is looking for fundamental disconnects. Like, it checks if the contract ID provided by the event actually corresponds to a registered contract.
Right, a contract not found exception. If it doesn't exist, that is a terminal error. The monitor cannot evaluate rules that do not exist.
Makes sense. It also verifies the internal architecture of the contract. The event might reference a valid contract, but ask to invoke a clause that isn't written into it.
A clause not found exception. Or it might attempt to pass a clause ID that technically exists in the database, but actually belongs to a completely different contract.
Invalid clause exception. And crucially, it interrogates the data arguments themselves.
Yeah, if the smart contract clause governing the taxi booking requires the passenger count as an integer, but the event payload delivers the text string 1 passenger, the fundamental structure of the data is incompatible with the programmable logic.
Invalid argument clause type exception. Or even simpler, if the clause requires 3 arguments, pickup time, location, and passenger count, and the payload only provides 2, the logic cannot execute.
Missing argument exception.
Yeah.
Exactly. If the event handler detects any of these structural inconsistencies, its reaction is absolute. It terminates processing immediately.
No second chances.
None. It associates the specific structural exception with the unique event ID and routes that failure directly to the system's event repository database. The journey for that specific event ends right there. It never even attempts to contact the blockchain.
Which protects the external network from processing garbage data.
Right.
But let's assume our taxi event is structurally perfect. The contract exists, the clauses align, and the data types are flawless. The event handler approves the payload. What next?
The event handler takes that approved payload, pairs it with all the necessary connection metadata it pulled from APIs 1 and 2, and pushes this complete package into the third component, the smart contract execution queue.
Another waiting room. But this one is positioned right at the edge of the system, facing the outside world.
Right, and the component pulling this queue is the heavy hitter, the contract invoker.
The contract invoker. This is the bridge between the internal monitor and the external distributed ledger. It pulls the fully prepped event from the execution queue and initiates communication with the target blockchain Ethereum or Hyperledger.
And this is where we have to clarify a vital technical nuance. We have established that the monitoring system as a whole operates asynchronously relative to the city's actual business processes, right? The taxi was booked, the traffic keeps moving.
Right.
But internally, when the contract invoker reaches out to the blockchain,
That specific communication is strictly synchronous.
yes, the contract invoker submits the data and the clause to the blockchain, and it must wait, holding its process open, until the blockchain network reaches consensus, executes the smart contract code, and returns a definitive result.
And that synchronous wait introduces massive vulnerability. Public networks experience latency spikes. Cloud-hosted consortium chains drop connections. What happens when the contract invoker asks Ethereum for a verdict and Ethereum simply goes silent?
This is where the parameter from API 4, the event retry policy, is activated.
Go.
The system designer's new network drops were inevitable. If the connection fails or times out, the contract invoker does not immediately register a failure. It utilizes a configurable retry mechanism. It takes the event and loops it back into the execution queue to be attempted again.
Right. The administrator sets that retry value. That they might configure it to retry 3 times for low-priority systems or 10 times for critical infrastructure.
Yeah.
It creates a necessary buffer against the unreliability of external networks.
However, if the event exhausts its NIN retries and still cannot secure a response, the contract invoker generates an execution category exception, specifically a blockchain connection exception, and terminates the effort.
But if the connection is stable, the smart contract runs its immutable logic on the blockchain.
Right. The ledger evaluates the taxi booking data against the rules. If the rules dictate that a hospital transit request must originate from an authorized subnet, and this request came from an unauthorized IP, the blockchain detects the breach.
The contract invoker receives this verdict and generates a contract clause violated exception.
Yes. And whether the execution resulted in a flawless validation, a connection failure, or a clause violation, the contract invoker takes that final state and pushes it to the fifth component, the smart contract outbound queue.
The final stop on the internal pipeline. And the sixth component, the event updater, monitors this outbound queue.
It performs the crucial final bookkeeping. It retrieves the ultimate execution result and formally links it to the original event record created when the payload first hit API 3.
And the paper details the exact structure of this final output generated for API 5 in listing 2. The most critical element of this JSON structure is a simple Boolean attribute labeled isValid.
And it evaluates to strictly true or false.
The logic governing that Boolean is completely unforgiving.
Mm-hmm.
The research dictates that an event is deemed invalid if any exception was raised at any point during its processing.
Right. If it was missing an argument back at the event handler, it's invalid.
If the blockchain dropped the connection 5 times, it's invalid.
If the contract clause was genuinely breached, it is invalid. The final output provides a categorized array of the specific exceptions, so auditors know exactly where the failure occurred. But the top-level validity is binary.
It is a brilliantly compartmentalized architecture. The queues isolate the components, allowing the event handler to process thousands of structural validations a second without being slowed down by the contract invoker waiting on a sluggish blockchain response.
It's designed for maximum throughput.
It is a phenomenal piece of theoretical engineering, but theoretical elegance often shatters when it hits the messy reality of actual software development.
Uh-oh.
The researchers didn't just publish the theory. They built the source code, which they made available on GitHub. And as they transitioned from blueprint to functioning prototype, they ran into significant roadblocks.
Real-world implementation always exposes the friction points. The paper candidly discusses 3 major challenges they are currently confronting. The first is what we can call the redundancy problem, and it centers on API 2.
This is the interface where administrators register the smart contracts.
Right. In the current iteration of the system, a human user has to manually input all the metadata, typing out the contract names, the clause IDs, defining the data types for the arguments.
Which the researchers correctly identify as highly inefficient, because the smart contract itself, the actual Solidity code residing on the blockchain, already contains all of this structural information.
It is entirely redundant data entry. You are forcing an administrator to manually summarize a piece of code that the system could theoretically just read itself.
So they're working on automating that.
Yes, their ongoing work involves developing mechanisms for the monitoring system to automatically parse the deployed smart contract code and dynamically infer the required metadata in clause structures.
Eliminating the manual bottleneck. That's a usability hurdle. But the second challenge they document is fundamentally more critical.
The security problem.
Right. This directly involves how the monitor manages cryptographic access.
Because to interact with a blockchain platform, particularly enterprise-grade or cloud-hosted ledgers like Azure Blockchain or AWS-managed networks, the contract invoker requires connection keys, access tokens, cryptographic passwords.
And these keys grant the holder the ability to interact with the immutable ledger governing the megacity. They are the ultimate high-value target for a malicious actor.
The paper explicitly acknowledges that storing these keys locally in the monitoring system's own database or file system is an unacceptable security vulnerability.
Yeah, if the monitor's database is compromised, the attacker gains unfettered access to the city's underlying blockchain infrastructure. Game over.
To mitigate this, the researchers are evaluating the integration of specialized third-party enterprise security solutions. They specifically reference Bitwarden, Azure Key Vault, and AWS Key Management Service.
These platforms are hardened, isolated vaults designed exclusively for the secure storage and lifecycle management of cryptographic secrets.
Right. Instead of holding the key, the monitor has to authenticate itself with the vault every time it needs to reach the blockchain, request temporary use of the key, and execute the transaction.
It adds a layer of operational complexity, but it is an absolute architectural necessity to prevent a catastrophic breach.
Exactly. The third roadblock, however, is arguably the most difficult to overcome because it isn't a technical problem, it is a human and logistical problem.
The formatting problem.
Yes.
This brings us back to API 3 and that perfectly structured JSON payload from listing 1. The monitor demands that every event arrives with the correct authentication header, the contract ID, the clauses, and the arguments flawlessly formatted.
And the theoretical design assumes the integration platforms will willingly generate this specific payload. But in a real-world megacity, you are dealing with a staggering variety of integration tools.
You have cutting-edge open-source microservices running right next to 20-year-old proprietary mainframes utilized by the municipal water department.
Exactly. You cannot issue a top-down mandate telling thousands of independent developers, corporate vendors, and legacy IT administrators to completely rewrite their core communication protocols just to satisfy the formatting requirements of your new monitoring system.
Because developers despise touching stable legacy source code.
Oh, they hate it. The risk of breaking a functional system just to add a logging feature is immense.
So the researchers analyzed how to bridge this gap between non-compliant integration platforms and the rigid API 3. They evaluated 3 distinct approaches. The first approach was the most direct. Update the source code of the communication ports directly within the integration platforms themselves.
Dive into the water department's mainframe code and force it to spit out listing 1 JSON.
Which they immediately discard.
Yeah, the effort required to understand and modify hundreds of disparate, complex external code bases is astronomical. And furthermore, it's a technological dead end because you can only modify open source platforms.
Right. If a city department is using a proprietary closed source integration tool from a major tech vendor, you legally and technically cannot alter its internal port logic.
So the direct approach fails.
What was their second option?
They considered building a massive conversion layer directly inside the monitoring system, sitting just in front of the inbound events queue. This layer would intercept whatever chaotic proprietary data formats the various city systems output and translate them internally into the standardized listing 1 payload.
I mean, this sounds far more reasonable. You put the burden of translation on the monitor, not the city. Why did they reject it?
Because it fundamentally corrupts the architectural philosophy of the monitor. If you build that translation layer, it has to contain custom logic for every single type of software the city uses.
Oh. And when the city adopts a new piece of software, the monitoring system has to be updated with a new custom adapter.
Exactly. The researchers firmly maintain that the monitor must remain entirely software agnostic. It should not contain custom logic detailing how to parse a specific vendor's proprietary log file.
It turns a sleek, agnostic referee into a bloated, customized nightmare. Which brings us to the third approach, the one the researchers successfully tested and recommend, utilizing the decorator design pattern.
The decorator pattern is a fundamental concept in software engineering architecture. It provides a mechanism to dynamically add new behaviors or responsibilities to an individual object without altering the code of the object itself.
Let me conceptualize this, because modifying behavior without changing code sounds contradictory. Let's use a physical analogy. Consider a smartphone. The original source code of the integration platform is the fragile glass and aluminum chassis of the phone itself. If I want to add a new behavior to this phone, specifically, I want to make it shatterproof when dropped. The first approach, modifying the source code, is the equivalent of taking the phone to a lab, melting down the glass, altering its chemical composition to be impact resistant, and rebuilding the device.
It is incredibly invasive, highly risky, and almost guarantees you will break the internal wiring in the process.
Developers refuse to do it.
It violates the integrity of the original system.
But the decorator pattern is the equivalent of simply buying a heavy-duty, impact-resistant rubber case and snapping it onto the outside of the phone.
Ah, wait.
I have fundamentally altered the behavior of the device. It now survives a 10-foot drop. But I have not touched a single atom of the original glass or internal circuitry.
That is a perfect visualization. In the context of our integration platforms, the developers do not alter the core business logic of their applications. Instead, they apply a decorator layer between the application's core output and the network port.
So when the municipal health system finishes its internal logic and prepares to send the taxi booking request, it outputs its standard proprietary data format.
The original software considers its job done.
But before that data hits the network, the decorator intercepts it. The decorator is specifically programmed to take that specific output, format it perfectly into the listing 1 JSON payload, attach the authentication header, and silently fire a copy to API 3 of the monitor, all while allowing the original data packet to continue to its actual destination.
The beauty of the decorator pattern is its non-interference. The original integration process is completely unaware that the decorator even exists.
Its performance and core functionality remain untouched, yet it is now fully compliant with the monitoring system's rigorous input requirements.
And the paper notes that their proof of concept utilizing this pattern yielded highly promising results, demonstrating a practical bridge between legacy systems and next-generation monitoring.
It is an incredibly elegant solution to a massive logistical roadblock. And it brings us to the conclusion of our analysis of this system. We started with a foundational problem. How do you enforce complex contractual rules across millions of automated software interactions in a megacity without slowing the entire ecosystem to a halt?
Right. We saw how the researchers proved that existing infrastructure monitors and AI diagnostic tools fundamentally fail because they lack the contextual awareness of blockchain-based smart contracts.
And commercial solutions are economically unviable at municipal scale.
Exactly.
We explored the massive philosophical pivot away from synchronous enforcement. The decision to abandon real-time blocking in favor of asynchronous monitoring prioritizes the operational speed of the city, accepting the reality that flawed transactions will occasionally occur and must be rectified later.
We dissected the highly modular decoupled architecture, utilizing message queues to isolate the high-speed structural validation from the high-latency blockchain queries.
Resulting in a system that is fundamentally agnostic to both the underlying software and the target ledgers.
And finally, we looked at the real-world deployment challenges, utilizing the decorator pattern as the critical non-invasive bridge to bring legacy municipal systems into compliance without risking catastrophic source code modifications.
It is a remarkably comprehensive architectural proposal. However, the researchers acknowledge their work is far from finished. The source material outlines specific future directions, most notably the necessity for rigorous stress testing.
They need to deploy the system under extreme, simulated high-demand usage to identify its absolute breaking points.
And there's a fascinating irony hidden in that future work.
What's that?
Well, the researchers hypothesize that the internal decoupled queue system of the monitor is actually so robust that it will easily survive the stress test. It is the external dependencies, the public blockchain networks buckling under the query volume, or the integrated applications themselves failing to generate events fast enough that will likely crash before the monitor does.
That is ironic.
They also note that while they dismissed artificial intelligence for the deterministic evaluation of contracts, they see massive potential for incorporating AI into the system's periphery.
Oh, sure. Machine learning algorithms could analyze historical execution data to automatically identify subtle misconfigurations in API 2.
Or predict cascading clause violations before they spread across multiple city services.
The architecture provides the deterministic foundation, and AI can eventually provide the predictive oversight.
Which leaves us with a final, profound implication to consider. It builds directly on the researcher's core philosophical choice, prioritizing asynchronous monitoring over real-time enforcement. By designing a system that evaluates rules in the background, transactions are explicitly allowed to execute before a smart contract violation is detected. The city's digital infrastructure prioritizes uninterrupted momentum. But as the researchers coldly state, this requires compensatory actions when a breach is eventually found. Think about the physical reality of that academic phrase. What does the logistical nightmare of a compensatory action actually look like when digital systems control physical infrastructure in a city of 15 million people?
It's staggering to think about.
Let's return to our opening scenario. The municipal health software automatically books a taxis for the elderly patient. That integration process runs smoothly. The physical vehicle arrives, the patient gets in, and they are transported across the city to the hospital. The physical action is completed.
Right.
But 40 seconds later, the asynchronous monitor, churning through its execution queue, receives a verdict from the blockchain. It discovers that the hospital's initial data request to the transit system violated a strict data privacy clause regarding the sharing of patient location data.
The contract invoker logs the event as a contract clause violated exception.
And the event updater flags the entire interaction as invalid. The smart contract has definitively caught a legal breach. But the physical action has already occurred in the real world. You cannot mathematically undrive a taxi.
You cannot untransport a human being across physical space.
If a chain of automated physical municipal actions executes based on an interaction that the digital referee later rules invalid, how do you compensate? Do you find the hospital? Does the transit system revoke the hospital's API access, potentially stranding hundreds of other patients? Who cleans up the physical mess created by an asynchronous digital mistake?
Because while the software architecture might be brilliantly agnostic and perfectly decoupled, the real-world consequences of those automated decisions absolutely are not.
Exactly. The architecture solves the problem of digital velocity, but it introduces a massive, unresolved tension regarding physical consequence. It forces us to ask how much physical chaos we are willing to tolerate in exchange for digital efficiency.
It is a question that engineers, urban planners, and ultimately citizens will have to answer as these invisible networks continue to expand.
Thank you for taking the time to explore this architecture with us. Keep questioning the invisible systems operating all around you. We'll see you on the next deep dive.